Hello students, I am Mahima Lahariya from Vijayanagar College Hospital. Welcome to my YouTube channel. Now we will start our today's topic, that is the analysis of the redox cycle. So I will explain this topic with the help of these two cycles. That is our first cycle, you can see this is for the hydration of the metal, and second you can see with the hydration of the hydrogen gas. So as we have already studied our Born-Haber cycle for the sodium chloride, like that those cycle only there. In this topic we are going to calculate the free energy changes in both the cycles. That is, in the first, the hydration of metals, how much heat is evolved, and how much heat is evolved for the hydration of the hydrogen gas. So now let us start our topic in details. So we can say that the redox cycle is used to calculate the electrode potentials thermodynamically. So we have already know what is the thermodynamic relations between the electrode potential and the Gibbs free energy. We already know the relation, that is our delta G naught equals to minus NF E naught. So we can if we know the value of our free energy, we can easily calculate the value of our electrode potentials. So to explain this, we can see the any example of the reduction of the metals, and we know to find out the reduction potentials of any metals, we couple the electrode with the reference hydrogen electrode, and we already know that the electrode potential of that hydrogen is arbitrarily fixed as 0. So now let us see the reactions involved in this process. That means our metal ion will react with the hydrogen gas to form the solid metal ion, and it will give us the H plus ion. Now in this whole reactions will be explained with the help of the two cycles. In the first step, we will see the hydration of the metal. Means our metal was in the solid state, it will convert to the aqueous state, and our hydrogen gas is first, it is in a molecule, it will dissociate into atom, then it will change into the gaseous ion, then it will convert to the hydrated, means in the aqueous state. So H plus. In both these steps, the heat involved in the first cycle is the Q1, and it is the Q1 is the total heat involved in the hydration of metal, and Q2 is the total heat involved in the hydration of the hydrogen gas. So in the first cycle, hydration of the metal takes place and the heat evolved is Q1, and in the second cycle, the hydration of the hydrogen gas takes place and the heat involved is the Q2. So by adding the Q1 and Q2, we can easily get our free energy changes for this reaction. So we will put the value of our free energy in our relation, that is our delta G naught equals to minus NFE. We can also write in the form as for the electrode potential, that is E naught equals to minus delta G naught upon NF equals to, by putting the value of delta G as Q1 plus Q2, we can write it from the equation number first, our value, that is the free energy changes, the sum of Q1 plus Q2. So we can substitute this value in this equation, so we can get E naught equals to minus Q1 plus Q2 upon NF. So with the help of this equation, we can easily find out the electrode potential of any metal, reduction potential of any electrode. So now to explain this, we have to first study the first cycle and then the second cycle, and by combining both the cycles, the heat involved, we can find the free energy changes, and we can calculate the value of the electrode potential by using the redox cycles thermodynamically. So we can say that what is the redox cycle main purpose? We can calculate the electrode potentials thermodynamically with the help of our redox cycle. So now let us start the analysis of the first. Now we will study our first cycle. It involves the 3 steps. That is, the first step, the solid metal convert into the gaseous state, and this gaseous state convert to the metallic cation state, and this cation, when interact with the water, it will get converted to the aqueous state. So let us see these 3 points, what type of energy involved and what the heat changes takes place in the details. So first step is the heat of sublimation of the metal. Means we can say that the solid metal get converted into the gaseous state. So the amount of heat involved to convert this solid metal to the gaseous state is termed as the sublimation. Means the amount of heat required to convert the solid metal into the gaseous metal. This is known as the heat of sublimation. It is denoted by delta SH. And we can say that what is sublimation? It is a process of conversion of the solid directly to the gaseous state, and here it is denoted by delta SH. Now second step involved is the conversion of the solid to the gaseous state. So we already know the first step, the heat involved is the delta SH, and the second step is the heat of ionization. So we will supply the ionization energy. What is ionization energy? Ionization energy is the amount of heat energy required to remove one electron from the outermost shell of an isolated gaseous atom. When we are removing one electron from any metal, we have to give the energy because the electron is attracted by the nucleus. So to remove one electron and to convert this metal to the cationic state, means by removing one electron we will have the +1 charge. So the amount of energy required to remove one electron from the isolated gaseous atom is known as the ionization energy, and we will get our metal cation in the gaseous state. Now we have to convert this gaseous into the aqueous state. So we will just react this our metal cation with the water, and this will convert to the metal cation in the aqueous state. Means when a gaseous ion is formed, it gets hydrated in the aqueous solution. Means when we react it with the water, it will get converted to the aqueous state, and this is the heat evolved in this step will be the known as the heat of hydration or the enthalpy of hydration, and the sign will be the negative. In the first two steps, heat of sublimation is positive, and the heat of ionization energy is also positive, and the heat of hydration is negative. So now we can see these three steps obeying the Hess's law. First step is our conversion of the solid metal to the gaseous metal with the help of the heat of sublimation. Then it get converted to the cation with the help of the ionization energy, and this gaseous cation gets converted to the aqueous cation with the help of the heat of hydration. So the total heat involved in the three steps is the Q1, or we can also say that the Q1 is the sum of delta SH, then ionization energy, and our delta hydration heat. So this is for the first cycle. Now we will see the second cycle. Second steps, that is the hydration of hydrogen gas, also involves the three steps. The first step is the conversion of our H2 molecule into the hydrogen atom in the gaseous state by supplying the heat of dissociation. So we can see in the cycle also, first our hydrogen molecule, gaseous molecule is getting converted, dissociated into the hydrogen atom. Then from this gaseous hydrogen, we will eliminate the electron by supplying the ionization energy. What is ionization energy? It is the amount of energy required to take one electron from the isolated gaseous atom. So this gaseous atom will lose one electron and it will get converted to H plus ion in the gaseous state. And when this gaseous state H plus ions will react with the water, interact with the water, it will get converted to H plus aqueous ion. So what is this? The amount of heat evolved in this process will be the heat of hydration, that is delta hydration H. So this is the overall cycle, and this cycle is also according to the Hess's law. Means what was our Hess's law? The total amount of the heat evolved, that is the Q2 here, will be equal either the process complete in the single step or either it combines in the three steps. Means the total amount of the heat will be the Q2 in this cycles. So what is the Q2? It is a total heat involved in the hydration of the hydrogen gas. Hydration means addition of the water to the hydrogen gas. So the main conclusion of this cycle is that we have to convert our H2 gaseous into the H plus aqueous ion. Now we can see these steps in detail. That is, the first is the heat of dissociation, and the heat of dissociation is symbolized as delta H dissociation, and we can just say that molecular hydrogen gas is converting into the atomic hydrogen. And what is heat of dissociation? It is the amount of heat required to dissociate 1 mole of gases into the atoms. Then what is the heat of ionization? In the second step, it is getting converted into the H plus gaseous atom. So when we remove the electron from the isolated gaseous atom, the amount of ionization energy supplied, it will get converted into the H plus. Then third is the heat of hydration. When these gaseous ions will interact with the water, they will evolve the heat of hydration and they will get converted into the H plus aqueous ions. So this is for the second cycle. So the amount of heat involved in the second cycle is Q2. Now we will see the sum of both the, now we will add both the heat evolved, that is Q1 and Q2. In the first cycle, it is the hydration of the metal solid to the aqueous ion, and the second cycle tells us about the hydration of the hydrogen gas. Now we will see the combining both the cycles, we will get the value of the free energy. Now we can say that by combining both the above cycles, we can calculate the energy used in the reduction of the metals. That is, we can calculate the Gibbs free energy, that is the delta G naught. Now we can see the first cycle, that is the first our metal in the solid states, by the heat of sublimation it is getting converted into our gaseous state, metal into the gaseous state, and by supplying the ionization energy it get converted into the M plus ion. It loses the electron and get converted to M plus ion in the gaseous state. And by when this gaseous metal cation interact with the water molecule, and by evolving the heat of hydration, that it get converted to the metal ion in the aqueous state. When this metal ion in the aqueous state react with the hydrogen gas, they will give us the metal solid and the H plus ions in the aqueous state. So how these H plus ions in the aqueous states are formed, we can see this reverse cycle from here. This is H2 molecule get dissociated into the H atom in the gaseous state. By supplying the ionization energy, this gaseous state hydrogen atom will get converted to the H plus ions, and this gaseous ions when interact with the water, they will evolve the heat of hydration and they will get converted into the H plus aqueous ion. So when we will combine both these cycles, we know the heat of hydration, the total heat involved in the hydration is our Q1, and the total heat involved in the our hydration of the hydrogen gas was the Q2. So when we'll combine both these together, we will have Q1 plus Q2, and this Q1 plus Q2 was our delta G naught. So we can calculate the delta G naught by putting the value of Q1 and Q2, which we will get from these cycles. So we can say that our relation, thermodynamic relation, is that delta G naught equals to minus NEF. So by putting the value of delta G naught, we can have the values of our reduction potential. So we can write this relation as E naught equals to delta G naught upon NF, E naught equals to minus delta G naught upon NF, and equals to minus Q1 plus Q2 upon NF. So we will get the values of our electrode potential of any metal. So we can just conclude that electrode potentials may be calculated thermodynamically by using this above cycle, and this cycle is known as the redox cycle. And we can just see the characteristics of the redox cycle. Now we will see the characteristics of the redox cycle. So the first point, the negative values of Q1 plus Q2 shows the spontaneous reactions, that is, it will go on, means the redox reaction is possible. Then second point, the positive values of Q1 plus Q2 indicates that it is a non-spontaneous reaction, or that reaction is impossible. So the negative values of Q1 Q2 shows spontaneous reactions, and positive values shows the non-spontaneous reactions. Third point, the negative value of electrode potentials shows the non-spontaneous reaction, that is, the reaction can occur in the opposite direction. Or we can say that the positive values of E naught shows the spontaneous reactions. So if the negative values are there, so the reactions are non-spontaneous, or they will take place in the opposite directions. Positive value shows the reactions are spontaneous. Then the fifth point, electrode potential depends upon the energy of ionization. So we already discussed what is the energy of ionization. It is the amount of energy required to take one electron from the outermost shell of an isolated gaseous atom. So if our standard electron potential values are high, then the ionization energy will be less. Or we can say that if the reduction potential values are less, the ionization energies will be very, very high. So we can see these values from our first alkali metals group. Now we have just written these values here in the table. So see, so we know the metals name: lithium, sodium, potassium, rubidium, and the cesium. Their values you can see just once. It is the free energy values for the lithium is 282, 254, for the sodium 262, 265, 269. Similarly, their experimental and the calculated value of the electrode potentials are written here, and their ionization energies values. So we can see from this table that first the lithium, the values are the highest ionization energies of the lithium, that is 519. So if we talk about the standard electrode potentials of the lithium should be inversely proportional to the ionization energy. So if ionization energy is high, so this should be less. But in this table, what we see this, the value of electrode ionization energy of the lithium is maximum, and its reduction potential value is also minus 3.04. So how is it possible? So we can say that ionization energy of the lithium is maximum, that is 519, so its reduction potential should be minimum, but we found it to be very high, that is minus 3.04, and it is also acting as a strongest reducing agent. But how we can explain? So we can explain this property with the help of our hydration energy of the lithium, that the hydration energy of the lithium is maximum because of its small size. So because of the hydration energies values, its reduction potential is also more than the other alkali metal. So with the help of our hydration energy, our redox cycle, we can explain the lithium, the values of reduction potential is also more than the comparing with the other alkali metal, and it is also acting as a strong reducing agents. So the last characteristics, the reduction potentials of the halogens are positive. The halogens have the positive values of the reduction potentials. I have already discussed in the electrochemical series. So now this is sufficient for the redox cycles. So I hope you all understand this topic well. Thank you for watching. Please share and subscribe my channel. Thank you.